of these problems. Okay, so this is a problem 19, and what is the name of this compound? And you can see that cobalt with ammonia, we call the aminin, and they are plus. Okay, and this is the one that is a negative, and the negative is also containing the metal. And this metal in the positive cation side, you just put cobalt as a cobalt, whereas a platinum on the negative side, you call the platinum with an ATE at the end. So how this name come about now is, I guess a 4 means tetrachloro, right? So that's a tetrachloro. Platinum, so platinate. That's the one. And then what do you do is now, okay, so then what do? I need to figure out the charges here. And this one is +4, -4, and there are 3 of them. Okay, and then this is a platinum. So I don't know that will be what will be the charges here, but it will be a x -4 plus multiplied by 3. So that's the charges. Okay, and I can do a little cheating here because the platinum has a +3s here, +2. So I can see that actually the charges on this, I just wanted to expedite the process. I can solve this problem, but I will just say that this is a +2, that's a -4, so make it -2. So the whole charges here is a -6. Okay, because that's a -4 here, and so on. And so that makes it, this is 6 charges, and then you need the two of them. So this means that you need the cobalt is 3 plus. To make 3 times 2 is a +6. Okay, so the cobalt is +6. So platinate is a +2, whereas the one goes in front is you have a hexaimini. So look for the hexaimini cobalt. So that's good. And then you are looking for tetrachloroplatinate. So this ATE coming from when you are in an anion, negatively charged ion form. Okay, the metal is this is a cation form. This is much more common, so they just put the name as it is. The number 20 is a question about the linkage isomer. This is the one that I mentioned to you about just before in the crash course part B. And when you have a linkage isomer, it means you have a ligand there's 2 different possibilities of different atoms can form the docking with a central metal, right? So these are the 2 possibilities. And so here is an example of nitro and nitroso, and then there's the nitrogen lone pair is on the nitrogen side. They are forming the docking of the central metal, or the oxygen, there's a lone pair, they're forming the docking of the central metal, right? So this is a case where where the linkage isomer is those one. And this meaning trying to show it to you that, okay, nitrogen shown up here, one oxygen shown up here is they are the one having the lone pair electron, essentially making a docking to the Fe. It looks like a distance, but 3-dimensional structure, they are the one neighboring to each other. Number 21 is a chiral isomer, and then I discussed this one before, and there is in the part B2, an example of MnEn3, or the metal with En2 with, let's say, bromine 2 or chlorine 2. Okay, these are the one. This is actually not always, only for cis. Okay, if somebody has a cis octahedral, that could be also, they can both have an optical isomer. Okay, so that's the one that you can find out. So which complex ion is a chiral isomer, optical isomer? Octahedral, the one with 3 diamine, ethylene diamine, is the one that can form the chiral isomer. Number 22, which is wanted to do, the d orbital of transition metal, they find out this kind of splitting. What do you see? You see this in between orbital has a higher numbers, right? So energy splitting is now 3 in between dx, dy, dz. I think this one, I think that Dr. Ma made a mistake. It should be an xy, yz, and xz. Okay, so that's the one. And then the one in the bottom is dx, dg2, and dg squared and x squared. So this is the one what we call the delta tetrahedral, because the go in between is the one that higher end, right? The other one higher end. So what the tetrahedral is coordination geometry for this energy splitting. This is also, I covered that in the energy splitting diagram. Number 23, which complex ion absorbs the light? Oh yeah, so okay. There's a student that Colette, you probably your microphone is on. So I can hear you. You can, if you mute yourself, that would be great, because I can hear you. Colette, yeah. Don't get scared. I think that you can see your microphone button. There's a red sign with a muted, and I think that will be fine. Okay, so which complex ion absorbs the light, and whether there is an energy splitting. So let me just say this is a tetrahedral, octahedral. So this is going up and down. Anyway, this is an energy, and the energy gap is absorbed by the light. And you remember this is the light is absorbed by this split energy diagram, and that energy is h nu, h c over lambda. So the higher the energy are, the shorter the wavelengths. Okay, so that's the one thing that I hope you still retain from the Chem 1 first week class. We talked about photo energy. So the higher energy gap, the one with strong ligand in inorganic chemistry term, right? And what do we say about the strong ligand? CN. This one is a very strong ligand, right? So that's the one that I can hear. This one. Okay, so complex ion, blah blah blah, and has an absorption lambda max. So the lambda is 463 nanometers. And what is a crystal energy splitting in kilojoules, right? So it's the same thing. Energy is hc over lambda, and you just have to put those numbers. And h is a Planck constant, and the Planck constant you have to look at from Okay, so I can do it. Okay, so let's stay with me for a couple of minutes, and let me finish this. So 6.63 10 to the minus 34 joule second, and the speed of light is 3.0 10 to the 8. So I'm just using the meter base unit. The lambda is 463 10 to the minus 9, which is a meter, right? And this one, essentially, what you have seen here is, wait a minute, this is energy for one photon. But what they're saying is per mole. So you need to multiply this artificial term called Avogadro's number, which is a 6.02 10 to the 23. And if you have them everything together, you'll find out 2.6 10 to the 5 joule per mole. Okay, and that's the B is the answer for this question. The number 4 is the last one, and then how many unpaired electron? I don't like this problem because this should say in d orbital. Okay, would you expect from the complex ion of cobalt OH6? 3 minus. So the most important information is OH hydroxide, which is a hydroxyl in the nomenclature, has a minus charges. There are 6 of them. So minus 6 charges from this side, and therefore your cobalt should have a plus 3 charges. Okay, so we are talking about cobalt with a 3. And then the cobalt, if you're looking at your periodic table, the cobalt is in here. Cobalt is Z is 27. Okay, and then it will have a cobalt. Okay, so I look at the cobalt now. You guys can see that. So if you look at here, that's a cobalt. Where is a cobalt here? That's right here. That's a number 23 in the periodic table, and so that's essentially having 4s2 D7, 3d7 with argon, and then we became the cobalt 3 plus, means argon with, this is gone, and this we're going to lose one, so 3d6. Okay, so they are just saying the same thing again here, saying that we have a 3d6, so we have a 3d6. D orbital has a 5 degeneracy, 1, 2, 3, 4, 5, 6 electrons. So how many unpaired electron? 4 of them. So therefore, how many unpaired electron in there? 4 unpaired electrons. So this molecule is a paramagnetic. Okay, I think that I did a little